So this is NURS 2533, Process of Human Disease 1. So this presentation is for Unit 3, Inflammation, Immunity, and Infection. This is Part 1, Inflammation. Now, this is all covered in your textbook, chapters 8, 9, 10, 12, 40, 45, and 52. It's probably a good idea that when you're reading these chapters to refer to the syllabus to figure out what's important so that you can tailor your readings to the topics at hand. You'll notice that in the syllabus, um, many of these chapters are in various units. So you'll end up covering it all, but or most of it anyways. But for each specific unit, there's only certain parts. So we're going to have a discussion of inflammation. Now, inflammation is a normal and often beneficial thing. It's a non-specific reaction to some sort of tissue damage, some sort of an insult, a pathological insult to the system. It can be systemic, but usually it's local. And the tissues are somehow damaged by a pathogen or trauma or by something like that. And then inflammation is the result. It's characterized by chemicals called inflammatory mediators that cause the movement of stuff from the blood into the damaged tissue. So that's mostly fluid and white blood cells. And it's necessary for healing, and it paves the way for fixing things up to return to normal structure and function. A story I like to tell about inflammation is one time I had a little rust hole in the door of my car, and I brought it to a body shop to get it fixed. And the guy took a grinder and he made this hole, which was about the size of, the size of a dime. And with the grinder, he took the paint off the door, off of most of the door. And then he made that little hole 10 times bigger. He ground away and cut away at that hole until the hole was much larger. Then he replaced the metal. He welded in new metal, and then sanded and primed and repainted the door. So why did he do that? Why didn't he just fill the little tiny hole? Well, what he did was he got back to good metal. The rust hole, there was the part that was the hole, but then the surrounding metal was infected with the rust. And so he had to enlarge that hole back to the good metal to make an effective repair so that everything there was good. And inflammation works the exact same way in our bodies. It's about prepping the area for a proper healing and for a proper repair job, so that the structure becomes normalized and the function becomes normal. Now we know that the suffix itis means inflammation, and it's probably one of the most common suffixes that we use because inflammation is so nonspecific. It's everywhere. So we tend to just use itis to describe the body part being inflamed. So tendinitis is the inflammation of a tendon. Tenosynovitis is the inflammation of a tendon sheath. Arthritis is the inflammation of a joint. Gastritis, inflammation of your stomach. Pancreatitis, inflammation of the pancreas. All of those things just literally mean inflammation and all that it entails. So, as I've just said, there are purposes to the inflammation, and it's a very useful and necessary thing. So, one of the things that it does, the first thing that it does, is it neutralizes and eliminates the pathogen, if that's providing the tissue damage is caused by a pathogen. So it isolates and neutralizes and then kills and removes the pathogen. Um, it limits the spread of the pathogen to other areas, so it keeps them all put. And it allows for tissue repair. It prepares for tissue repair. There are 5 cardinal signs of inflammation, and this is when we see these things, we know that there is acute inflammation. Uh, when I was in school, there was a mnemonic that was supposed to help us remember, and for literally thousands of years, it was considered that there was 4 signs of inflammation: redness, swelling, heat, and pain. And the mnemonic for it was rubor, calor, tumor, and dolor, which is red, heat, calor, swelling, tumor, and pain. And that was actually coined by a Greek philosopher named Celsius in the 1st century AD. So, and it stuck right until quite recently. Now, most authors consider that there are 5 cardinal signs of inflammation, the 5th one being loss of function or immobility. So the new mnemonic, which is much easier to remember, is PRISH, Prish. So that's pain, redness, immobilization, heat, and swelling. PRISH, Prish. Now, it's going to be important for you to understand what all of these things are about and be able to explain the presence of each of them and why they're there. But really, it all comes down to one fundamental fact. Inflammation, especially acute inflammation, is about bringing more blood to the area. We'll talk about it in detail in a second, but basically, more blood, the tissue gets red. More blood, more fluid, the tissue swells. Blood is warmer than other tissues, so more blood in the area, more heat. When the tissue gets stretched and the nerve endings get compressed, pain is the result. And tissue that is either swollen is immobilized, or if the tissue is damaged and it's not functioning properly, that's the loss of function or immobility. So, in a nutshell, Prish. So there's 2 types of inflammation. There's acute inflammation, which is very important. It's a very positive thing. It's short in duration, usually a week, 10 days, somewhat less than 2 weeks. And there's a set of events that we'll discuss that it happens in a sequence, and there's a purpose for the events. Now, what it's supposed to do is get rid of the pathogen and neutralize and eliminate the pathogen, limit the spread of the pathogen, and prepare the area for tissue repair. If it's not successful at doing those things, then what happens is the inflammation becomes chronic. So if the pathogen is hard to eliminate and it isn't being eliminated, if the pathogen spreads, if the damage is too much for normal processes of tissue repair, the inflammation can become chronic. So in chronic inflammation, the response is more diffuse, it's sustained, it lasts way longer. And the problem is that uh, it can itself lead to damage. Chronic inflammation is not a positive thing. Chronic inflammation will result in further tissue damage. It can result in scar tissue, uh, a permanent loss of function. So it can cause dysfunction in an organ. If there's loss of function in a tissue, then the organ is going to be affected. So chronic inflammation is not, it's something that we want to avoid. Acute inflammation, very, very important uh, as, as a stage of healing. So now, like I said, really what it is about bringing more blood to the area. And the blood vessels in that area become more permeable. Um, so, so bringing more blood to the area brings more nutrients, and it brings more leukocytes. It brings more white blood cells whose job is to deal with the pathogens. Um, the the leukocytes, which are the white blood cells, the first ones to arrive, as you know, are the neutrophils. Remember the never let monkeys eat bananas. So neutrophils are phagocytes that arrive first. Now, the neutrophils are in the blood. All the leukocytes are in the blood, and the damage is in the tissue and in the interstitial spaces of the tissue. So we have to somehow get the leukocytes from the blood out to the tissue. We have to get the all the tools that are necessary, all the things that are necessary out into the tissue from the blood. The blood brings it there. Somehow it has to get across. So there's a series of steps that that allow this, and we call this whole process the emigration of the white blood cells. Um, so the first thing that happens is when the white blood cells get to the area, the in the blood vessels now have changed because the inflammatory chemicals, and the endothelium reacts with the white blood cells and cause something called margination or pavementing. Now, the margination of the leukocytes is basically the leukocytes kind of going to the edge of the blood vessel, the edge of the capillary, becoming in contact with the endothelium, and sticking there and staying there, not being washed away quite as readily. So it's kind of a buildup of these white blood cells. There are chemicals called selectins that facilitate these leukocytes to get across and out into the tissue, into the interstitium. The process of actually getting across we call diapedesis, or to step across, step through, dia through, ped, foot. Emigration is also a term used. You'll see them. The term diapedesis is actually going out of favor, and emigration is coming more into favor, but you'll hear both of them being said. And then once the white blood cells have left the blood vessel and are now in the interstitium, they have to be transported to the area of damage, and that happens by following a trail of chemicals that are being released by the damaged tissue, the inflammatory chemicals that cause these white blood cells to move towards that area. And this process is called chemotaxis, uh, taxi by chemicals, uh, carried towards by a chemical trail. Now, and the next important thing, once these phagocytes especially get to the area, then they have to start eliminating the pathogens. They have to start cleaning up debris and that kind of thing. And that's uh, phagocytosis. Now, if this all works, what happens is, so the pro-inflammatory chemicals are released, which cause the vascular permeability increase, which allows and causes the emigration, the diapedesis. Their chemotaxis brings it to the area. The phagocytosis happens just because they are phagocytes. But if the insult is persistent, then what will happen is a lot of these white blood cells will almost take up residence and stay put at the site. And we call that a granuloma. It's basically the macrophages stay put. And to the point where the macrophages will almost lose their amoebic qualities, and they will start to look almost like epithelial cells. They will be doing the job at the area, but they'll also maintain the inflammation. Okay, so this is just a chart looking at the whole process of emigration. Please, I don't want you to worry about the biochemistry of all this, but mostly just the process. So, um, so what happens is the inflammation in the tissue. So this is the tissue area here. This is the inside the blood vessel. What happens is the inflammatory chemicals trigger a whole series of events. When the selectin, which is basically a protein on the endothelial cell, it acts as a receptor. The ligand that goes to that receptor is on the white blood cell. What happens is when the ligand meets the selectin, it causes it to kind of stick and then roll, and then the rolling makes another selectin called an integrin, make the thing stick. So this is so it adheres. So this is the whole pavementing, margination is happening here, and then the white blood cell squeezes out through the endothelial cells and migrates into the interstitial fluid of the tissue, and then follows the chemokines, the chemotaxis molecules to the site of the inflammation. So it just flows that way. This is actually a photomicrograph of a neutrophil undergoing diapedesis. PMN stands for polymorphonucleocytes. You'll notice that in the neutrophils, the nucleus has lots of lobes. So a lot of people that do blood work call them polys or polymorphonucleocytes because that's how you identify them. It's interesting that in the labs, they tend to call them polys. In physiologists tend to call them neutrophils. They're the same thing. And so you can see this actually squeezing through this which is the endothelial cell. So what's going on here? The tissue gets injured, and it can be injured by any one of a bunch of things, by trauma, by ischemia, by neoplasm, dysplasia, things like that, by infectious agents. And this is the one that that we will kind of concentrate on. By understanding how it does it with infectious agents, basically you'll understand everything, how it works with other things. But it can even be non-living things like foreign particles, asbestos, carbon, any silica, any of those things that we talked about when we talked about necrosis. But in any case, whatever the tissue injury is, what happens is the injured tissue starts to release inflammatory mediators. Now, healthy tissue that's functioning normally, releases kind of anti-inflammatory chemicals all the time that stop inflammation from happening. When the tissue gets damaged, it stops producing the anti-inflammatory chemicals and starts releasing the pro-inflammatory chemicals, the inflammatory mediators. And these mediators basically fall into two categories. There's the vasoactive mediators and there's the chemotactic factors. So we'll look at these chemotactic factors first, these ones over here. Basically, and please, we're not going to have you memorize them all, but they fall into this category where they attract cells, white blood cells especially, to the area of the trauma. Most of them are chemokines. Chemo, chemicals, kines, movement. So chemicals that cause movement. This C5a is one of the complement proteins that we talked about before in AMP when we talked about the immune system. So these chemotactic factors really cause the recruitment and kind of the activation of the cells. Now, for acute inflammation, the most common and the most important one are the neutrophils, but platelets and mast cells are also involved. And the mast cells release some of the vasoactive mediators. As it goes chronic, so these are kind of the innate. These are those more specific response, immune response cells, lymphocytes, plasma cells. So they're more involved with the specific of fighting the specific pathogen. And we see those in chronic inflammation. But all of this is triggered by these chemotactic factors. The other group are the vasoactive factors. And like the name suggests, they act on the blood vessels. Probably the most important one is histamine, which is a vasodilator, serotonin, the bradykinins, nitric oxide. These things are all involved with changing both the permeability and causing vasodilation. All of these together increase the permeability, increase the dilation, which then means that things leave and go to the interstitium. And edema is really that. It's this excess of fluid that is in the interstitium, in the interstitial space. So these two groups of mediators work simultaneously and they work together. So when we kind of sum it up, this is actually a nice little chart that does it. Injury causes the endothelium of the blood vessels to bind with neutrophils, the phagocytes, um, that will lead to emigration, which will lead to phagocytosis, and the phagocytosis will eliminate the pathogen. Injury causes the vasoactive chemicals to cause vasodilation, which brings more of this stuff to the area and increases permeability, which enhances emigration of the phagocytes, which increases phagocytosis. The chemokines, which are released by the injury, really cause this emigration and bring the involved with the chemotaxis and bringing the phagocytes to the area of trauma and cause increased phagocytosis. Ultimately, what we want to do is increase the amount of phagocytosis in the area because that's what eliminates the pathogen. So these factors all work together to give us the cardinal signs. Now, this book obviously uses the four cardinal signs: pain, heat, redness, and swelling, with the fifth one being immobilization or loss of function being connected to this. And probably the easiest thing, and to kind of sum this all up easily, it's all around increased vasodilation and permeability. So the tissue damage, the factors, the inflammatory chemicals get released. They cause vasodilation. Vasodilation causes redness and heat because blood is red and hot. Right? The vasodilation brings more blood to the area, and that, coupled with increased permeability, causes swelling. And the swelling and the vasodilation compress the pain receptors and cause pain. Now, some of these factors, actually, like prostaglandins, actually are pain mediators in themselves, so they directly cause pain. And really, pain is a useful thing because it prevents you from further damage. It makes you realize that something hurts. If you put your finger on a hot stove, the pain comes as you pull away your finger rather than keep on cooking it. Now, the neutrophil emigration contributes to swelling, and then the swelling really contributes to the loss of function, the fifth cardinal sign. So, so that's what we're seeing, especially in the acute inflammation. As a matter of fact, only in the acute inflammation. So this this acute inflammation is self-limited, and the whole idea is to return to function. What we want to do with acute inflammation is uh, remove the stimulus that causes the inflammation to begin with. Uh, Turn off these kind of pro-inflammatory signals. When we're finished with it, we want to stop this emigration and the influx, right? And then we want to restore the balance of fluids. We want to remove the cellular debris and get normal vascular functioning afterwards. In chronic inflammation, which persists, the tissue starts to get damaged by the inflammation itself, and it becomes kind of a vicious circle. And so we kind of get a distorted attempt to restore the tissue integrity, and it can lead to organ damage. So these cardinal signs of the acute inflammation are good. The chronic inflammation is the thing that we are more worried about. But there's an overlap, and we have to figure out where that the good ends and the damage begins. So edema. Edema is is the fluid leaving the blood vessel and going out into the interstitium. So with increased permeability, fluid and electrolytes leave, and proteins leave. And the proteins and the fluids and electrolytes together are called exudate. It's probably a good idea to come up with some definitions. So edema is moved into the interstitium of tissue. So when the fluid and electrolytes and proteins, the exudate, end up in tissue in the interstitial area, it is called edema. If the same thing happens, but the fluids end up in a body cavity, like the peritoneum or the pleural cavity or the pericardial cavity, we call this effusion. So we get pleural effusion is the same process, but into the cavity, and the cavity fills up. So the fundamental difference between edema and effusion is where the fluid goes to. Now, sometimes it's just fluid, low protein content, and it will still cause edema, but we call that transudate. And that's really just fluid. More commonly, it's exudate. And exudate has a higher protein concentration. There's more inflammatory cells. We see exudate in acute inflammation. Okay, something that is a common misconception, and the common misconception is that infection is indicated by inflammation. So a lot of people, therefore, think that they're synonymous. They're not synonymous. Infection usually has inflammation, but inflammation doesn't always have infection. You can have inflammation from any sort of tissue trauma, from um, from blunt trauma, from ischemia. Those are both very common causes of inflammation that are not involved with infection. So when infection happens, or I'm sorry, when inflammation happens, we end up producing this exudate. And what does the exudate do for us? Well, it provides the pathway for the leukocytes and the pro-inflammatory mediators to move around. It provides the fluid, and fluid going in the correct direction to for chemotaxis and emigration. This excess fluid will dilute any toxins that are produced by the bad guys, by the pathogens, right? And it brings raw materials for repair. It brings amino acids for protein synthesis by the fibrocytes. It brings glucose for ATP, for the increased metabolic rate. It brings vitamins. It brings all kinds of things out to the area that is in need. So for the most part, it is a good thing. Now you can imagine that the exudates are not always the same. So there's a couple of different types of them. One of them is called the serous exudate. And really, it is a watery, kind of straw-like thing. It, it's really almost interstitial fluid on its own. It's just an increased amount of interstitial fluid. There's no real strong cellular response. The protein content's on the low level. It's more of a transudate than an exudate, like it's crossing that line. Uh, we get this when there is virtually no inflammation. So very, very mild inflammation will cause a serous exudate. The serosanguinous exudate is watery, but it contains blood. Sanguine is blood. So serosanguinous, there are red blood cells that escape into the exudate. So this means that the blood vessel is a little bit leaky, and the red blood cells actually get across as well. And so it becomes pink in color. Another one is called fibrinous. And this has a lot of fibrin. Now, as you will probably remember from AMP1, fibrinogen will turn into fibrin in the presence of prothrombin and the whole coagulation process. When fibrinogen is turned into fibrin in the interstitium, what happens is the exudate ends up with this tangle of fibrin. It starts to almost clot and coagulate itself. It's thick, it's sticky. It happens in tissue damage that's pretty severe, and less to do with pathogen and more to do with damaged tissues, because it helps kind of bind that tissue. Now, the problem with this fibrinous exudate is that it can actually bridge tissues that shouldn't be connected, and we call this adhesion. So it causes adhesions. It may limit the mobility or the motion because of it. Now, the exudate that most people are probably familiar with is called purulent. Now, purulent exudate is kind of the crap from the war against the pathogen. So it contains the cellular debris of the tissue cells that are damaged. It contains a lot of white blood cells, so lots of neutrophils. It contains dead bacteria. It contains all kinds of things like that. It's usually indicative of a bacterial infection. And this purulent exudate is more kind of commonly known as pus. The spirit of inflammation is a lot of this with some liquefactive necrosis, and that really is pus. But this purulent exudate, it kind of like it's a gray line. Like, where do you stop calling it purulent and start calling it superfluous? Whatever. When there's a pocket of this stuff, it's called an abscess. And sometimes the purulent exudate itself will cause inflammation, which will maintain and really prevent healing. So when these abscesses form, it's usually a good idea to drain them. And this is why a lot of different medical procedures are about draining abscesses, about putting drains in at the sites of surgery. dental processes for dental abscesses are about draining the purulent exudate um, from the abscess to allow healing, to kind of turn off this pro-inflammatory stuff. So the suppurative inflammation is there's a lot more liquefactive necrosis, a lot more pus. This picture is of suppurative inflammation of a brain. It's caused by an infection of the brain by a pathogen. So this is meningitis. And it's probably hard to see here, but this area here has got liquefactive necrosis, and all of this here is suppurative inflammation. This is pus-filled space here. Yeah, and so it's a nasty thing. There's something called hemorrhagic exudate, and hemorrhagic exudate is really bleeding into the tissue. So the blood itself leaves the blood vessels and ends up in the tissue. So we get this when we have severe damage and a lot of inflammation. And one of the problems with it is that the inflammation causes vasodilation, which may enhance this. Everything in the blood escapes into the tissue. So proteins, electrolytes, all kinds of things end up there. So most of the time, inflammation is local. It happens where the trauma happens or where this site of infection. So when you get bit by a mosquito, the site of the bite is where you get the redness and the itching or pain and the swelling, the hot spot, all caused by increased permeability of the capillaries, right? Increased pressure on nerves. So this is the prish. I'm not going to reiterate it too much, but the redness, the heat, the pain, the swelling, the loss of function, the immobility, all results locally in this, the cardinal signs, the kind of the 5 indicators, as it were. But inflammation can also go systemic. It can end up everywhere in your body. And these are what the systemic effects are. Now, you will notice that none of them are very specific. And a lot of these things are kind of the signs and symptoms of a lot of different diseases, which are really systemic inflammations. So fever is a big effect. Fever can be really good if it stops the growth of pathogenic organisms. It speeds up healing. It's kind of like this positive thing, as long as it doesn't get out of control. Malaise or just feeling like crap is systemic inflammation. Fatigue, headache, loss of appetite, anorexia are all these systemic inflammations. And that's why we see these things in a lot of different systemic diseases. Now, systemic inflammation can go from being fairly mild being quite severe. When it gets quite severe, it actually turns into something called SIRS, which is systemic inflammatory response syndrome. And this is when all of these things go crazy and will actually lead to shock, and can be very, very, very dangerous. That it can um, it can be fatal, um, by a huge loss in blood pressure. Well, you can imagine if you get systemic vasodilation, then blood pressure is going to drop, and that's shock. Now, we're not going to spend very much time, especially in this unit, talking about SIRS, but nevertheless, it's something to know about. So, aside from the PRISH and the systemic, we need some diagnostic tests. And so, how do we know um, when there is inflammation? How can we do it with lab tests? So the easiest one and the most common one is when you do a complete blood count, a CBC, you can look at an increased amount of white blood cells, leukocytosis, the increased white blood cell count. And that is indicative that there's inflammation, because the inflammatory chemicals cause leukocytosis. They cause an increase in the number of white blood cells. Another test that they use to look at specific things, are the C-reactive protein, and you'll hear about CRP, elevated C-reactive, and what this is, a protein that's released by the liver and goes out into your body, and it is used kind of along with complement to enhance phagocytosis by increasing opsonization, by making the phagocyte be able to grab hold of the pathogen. It gives the handhold by the C-reactive protein binds with the pathogen, and then the phagocyte binds with the protein, and the pathogen therefore can't get away from the phagocyte. So by looking at increased levels of the C-reactive protein, that means that there are pathogens that are making this happen, and that would lead to inflammation. Another important test is ESR, erythrocyte sedimentation rate. Basically, what this is how quickly do the red blood cells settle in a tube of uncoagulated blood. If they settle quickly, then that's indicative that there's more fibrinogen in the blood. Now, fibrinogen will lead to fibrin, and fibrinogen production goes up in inflammation because it may be needed. So this is kind of a side effect. Now, the ESR is not indicative of anything in specifically, but rather it is more indicative of pointing to inflammation, especially systemic inflammation. So a lot of the inflammatory diseases like polymyalgia rheumatica will see an elevated ESR. Every time you see an elevated ESR, it doesn't mean that the patient has polymyalgia rheumatica, but everybody that has polymyalgia rheumatica will have an elevated ESR because it's an inflammatory thing. Now, some of the other tests look at various enzymes that are indicative of inflammation in a specific organ, like the liver enzymes, AST, ALT. When they indicate liver inflammation when we see these isoenzymes in the blood. and they show up in blood work. If you end up in a merge or working in a place like that, myocardial infarction, one of the things that they do to see if there is inflammation of the cardiac muscle is they look for troponin 1, which is an enzyme that we see when the cardiac muscle is inflamed. So really, this is inflammation in a nutshell. What inflammation does is it sets the stage for healing. It isolates pathogens and it facilitates the elimination of those pathogens. And in that case, it's a good thing. Acute inflammation is short duration, self-limited, and and is useful for eliminating the source of the inflammation. You remove the stimuli. You basically set the stage for healing. Chronic is when it's persistent and it starts to cause tissue injury itself. And really, it results in a disorganized chance of restoring tissues to their function. And so it leads to organ damage. So the chronic inflammation is what gives inflammation a bad name. Where acute inflammation turns into chronic inflammation is a real gray area. And so it's up for a lot of discussion as to kind of at what point do you intervene with inflammation. Okay, the last part of this is about healing, and healing by first and second intention. And what does that mean? So healing by first intention happens in a clean, uninfected, limited wound, like this one. Surgical incisions tend to be first intention. Cuts are first intention. What happens in first intention, healing by first intention, is the cut goes down through to the tissue. Oftentimes, first intention, you get a suture. You get stitches, and what happens is the edges of the wound are brought together, either naturally by the action of the contraction of platelets in the wound, or by stitches, by sutures. Initially, there's hemorrhage. The wound gets filled with blood. It seals the wound so that you don't lose fluids out the wound. You don't let infections in. You get acute inflammation in the first couple of days, and so that's indicated by neutrophils surrounding the clot. So these blood vessels, diapedesis, the neutrophils come to the area, and they start phagocytizing the clot. Within a couple of days, then the neutrophils get replaced by macrophages because they are much better at cleaning things up. They're much bigger eaters. Now, at kind of this third day and on, what happens is the epithelium heals and kind of covers over. So as the scab, the clot is removed, then that allows the epithelium to bridge over and seal the wound, as it were. And so that usually happens within about two or 3 days. By 4 or 5 days, you got a kind of a multiple layer epidermis happening. It's it starts to go away. So then the fibroblasts in here start laying down collagen fibers to bridge the wound in the connective tissue layers. New capillaries start to grow into the area, right? And then scar is formed. And so these collagen fibers bridge the gap, and we end up with kind of back intact blood vessels and a little bit of scar tissue and the epithelium completely healed and normal. The scab falls off here as the epithelium pushes up and the scab gets removed, and that's first intention. There will be a scar, but it will be minimal and it's very straightforward. Now, the second intention healing happens when the wound is large, when there's a lot of tissue damage removed, or if there's infection, so if it's complicated with infection. You can't put stitches in this, so sometimes debridement is necessary, removal of damaged tissue. We get this kind of thing in like road rash or burns or things like this. There's way more to bridge. Now this takes a while to heal. It's slow, and you get some large, ugly scars can happen because of this. There's more inflammation in this kind of thing, and there is tissue called granulation tissue. Now, there's granulation tissue in first intention, but it tends to be a small amount, replacing the blood clot. In second intention, the amount of granulation tissue is far more. The blood vessels, new capillaries grow into the granulation tissue. It becomes very highly vascular. This is that, if you've ever seen it, it's kind of like a pink, like if you pick a scab off, you will see this pink and there will be a little exudate come out of it. That's the granulation tissue. Now, what happens is the fibroblasts start laying down. It replaces the granulation tissue with scar tissue, but the scar tissue is far wider. And when the scar tissue contracts, then it causes the epithelium to dip and has that characteristic kind of surface look at the scar. When we have something like this, first intention, most of the time, like hair follicles and other structures probably aren't damaged, and it heals up, and it's sweat glands and everything are fine, and everything is fine here. In second intention, this area has an epithelium that covers it. This area is all scar tissue, but you don't get the hair follicles replaced. You don't get the sweat glands replaced, and this scar ends up looking more like a bad old scar. So that's it for this section.